Hi, my name is Rachael Turner, and I'm a student at Binghamton University. I had the privilege of doing the Hunter College SPUR program this summer, where I researched the synthesis of a sequoring C derivative of sstepholidine as a potential dopamine D3 receptor antagonist. So a little bit about the field that I was working in this summer is the medicinal chemistry field, which, as you might expect from the name, integrates knowledge from both chemistry and pharmacology. We're specifically focused on the actual design and synthesis of novel molecules that can be used for future pharmaceutical use. What our field requires is a lot of integration of knowledge from neuroscience, biology, and organic chemistry. The lab that I work in focuses on synthesizing CNS ligands and psychoactive drugs, and that requires us to have a pretty in-depth knowledge of neurologic receptors and how our molecules would affect these receptors. We also need to be able to understand how these molecules would affect the rest of the body, because they need to be safe for human consumption in order to have pharmaceutical viability. A little bit about the connection between drug abuse and dopamine receptors. So as many of you may know, dopamine is a neurotransmitter, and it's typically implicated in the reward pathways. There are 5 types of dopamine receptors, D1 through D5, but we're specifically going to look at D3 in this study because it's been shown by previous studies that D3 receptor expression is actually increased in those with chronic exposure to cocaine and cocaine abuse. This increased abundance of D3 receptors makes it more likely for someone to relapse after they have quit the drug, and even harder to quit the drug in the first place. We believe that synthesizing something that's a D3 receptor antagonist, so an antagonist is something that blockades a receptor and doesn't allow the normal ligand to bind. So the normal ligand in this case would be dopamine, and it can't bind if we have an antagonist, and that would be effective at combating cocaine addiction. Not only would this prevent future cognitive impairment from continued use of the drug, but it also has the potential to reverse cognitive impairments already caused by the drug in the past. So why are we talking about this molecule sstepholidine I mentioned in the title? So sstepholidine is a THPB alkaloid, and all that really needs to mean to you is it's this tetracyclic 4-ring structure here with these 2 methoxy groups and 2 hydroxyl groups, as well as the nitrogen. They all may have implications in the affinity for the receptors. Currently, sstepholidine has an affinity for D1, D2, and D3 type receptors. However, we want to selectively get it to have better affinity for just D3, because D3 is what's implicated in cocaine abuse and addiction. So sstepholidine has been seen to have a reasonable affinity for this receptor at low concentrations. However, it's still not potent enough to be used as a drug for pharmaceutical use. So what the lab I'm working in has been focusing on is doing different substitutions on this molecule and seeing which functional groups are actually necessary for affinity and which ones we can replace to increase affinity and optimize its activity as a drug. My hypothesis is that a flexible analog of sstepholidine will actually afford the greatest D3 receptor affinity and selectivity, and that's what's going to end up having pharmacological implications in combating cocaine abuse and addiction in the future. We think that the best method for this synthesis is to do a 6-step process where vanillin is our starting material. So why a flexible analog, and what exactly am I talking about when I say a flexible analog? So on the left you can see our original molecule, and on the right that's our target analog, which isn't very different from the original molecule. The only difference is that we've cut ring C here now. So having cut ring C, this allows for a lot of flexibility. Rather than a rigid ring there, you now have a single sigma bond which can rotate around and the molecule can change conformations. This ability to change conformations will make the molecule, we hope, bind to the receptor more easily, because there should be less steric strain, more ability to fit to the shape of the receptor, so to speak. Not only will we synthesize this analog, this allows us to use this as framework for future analogs like we're using sstepholidine now. So we can do additional substitutions and add different structures onto this flexible analog, and that'll allow for an even greater catalog of molecules that we can test. So as far as the actual method that we're going about synthesizing this molecule, as I said, we start with vanillin. And vanillin has 2 reactive groups. It has that hydroxyl group and the aldehyde group. We don't want the hydroxyl to react. We want to keep that intact. So the first thing we do is we use a Williamson ether synthesis to add a benzyl group, because benzyl groups aren't very reactive, whereas the hydrogen would be very reactive. So now we can react with our aldehyde, and we start to build our framework for the second ring. This is what's called a nitroaldol or Henry reaction, and we make this nitrostyrene here. The next step is to reduce this nitrostyrene using lithium borohydride, and now you really start to see the second ring forming. The next step is to close the ring, which we're using what's called a Pictet-Spangler reaction with formaldehyde to do, and then you have our ring B. The next step is to do reductive amination, which is basically when you combine the two-ring structure that we have already, and then start synthesizing, or start combining it and making the sequel ring C and the D ring. Now you notice this compound looks a lot like our target analog. The only step left is to cleave those benzyl groups and make it so you restore our hydroxyl groups. We did explore other methods before we tried this method of synthesis, and that was when we used this starting material, our dimethoxy compound. And we wanted to use this because not only is it commercially available, it also would have replaced our first 4 steps of the reaction pathway that I just showed you with only 2 steps. Those 2 steps arise from the differences between this molecule that I'm showing you here and the 2-ringed molecule I showed you on the other slide. With this molecule, you have 2 methoxy groups instead of a methoxy group and a protected hydroxyl. So what we wanted to do was selectively cleave one of those methoxy groups, which is where we were hoping to use BBr3 or a similar compound, and then protect it with TBDPS. TBDPS is analogous to a benzyl group. They do have the same function in this, which is just protecting that hydroxyl. Then we would have continued with steps 5 and 6 of that synthesis, and it would have been much shorter and theoretically much easier. However, we encountered some problems, that we were only recovering the starting material from our reaction mixture, which meant that the reaction wasn't actually occurring. So we think this is because our starting material wasn't actually sold as seen on the screen here. It was sold as a protonated salt version of it. So it was an NH2 plus there, and that makes it pretty insoluble in any organic solvent that we would be using, and it makes it so it's not easy to react with. So we went with our better known chemistry. The lab that I'm working in has already done many steps of that synthesis, so we knew what we were working with, and that's the 6-step synthesis is what we proceeded with. How do we evaluate our reaction success and progress? Well, first, we used thin layer chromatography to tell us whether we had reactant left in our vessel, product, or a mixture of the two. Once we were sure our reaction had gone to completion and there was only product left, that's when we started the isolation process. So we would use many different techniques, including acid-base extractions and vacuum filtration. Then, if our compound wasn't pure, we needed to use purification with column chromatography or preparative TLC, both of which use the differences in polarity between 2 molecules to separate them out, because they'll elute at different times because they have a different affinity for the column. Then we would use hydrogen and carbon NMR in combination with mass spectroscopy, and we would assure that the actual right product was formed. It wasn't just a product that we weren't expecting. As a final measure, we would use melting point determination, which the range of the melting point would tell us a little bit about purity, and the actual value we could compare to literature values if there were any, and that would tell us whether our compound was, that would give us some more clues about the compound identity. So as far as where we are now and where we want to go, we do believe that the 6-step synthesis is the synthesis that's going to work better, and we've come to that conclusion. However, we're currently stuck on reaction number 4 of that, the ring closure reaction that you see here. So the first 3 steps, everything in green, has been completed already. However, our barrier is kind of reaction 4. We may have completed it today. I'm waiting on NMR analysis, but we don't anticipate many problems with 5 or 6. So we anticipate being able to synthesize this molecule no problem in the future, and then once we do, we'll continue to synthesize additional analogs with substitutions on that, or changing that reductive amination step where we add that D ring. We could do different derivatives of that D ring or different other rings even attached to that, and make a whole library of analogs that can be analyzed in structure-activity relationships. So that's what we're going to do once we get significant quantities of these, then we'll send them out for structure-activity relationships, and that will tell us if they have pharmaceutical viability in the future. I would like to acknowledge my mentor, Dr. Wayne Harding, as well as my lab mates and the Hunter College SPUR program and our sponsors.